In the Clarion-Clipperton Zone in the Pacific, deep beneath the ocean's surface lie billions of potato-sized rocks called polymetallic nodules. They contain nickel, cobalt, copper, and manganese, the metals we need to meet the demands of a growing urbanized population and for a clean energy future. But reaching them isn't easy. Blue Nodules has partnered leading academic and industry figures to further develop the technology to mine these nodules from the seafloor with minimum environmental impact, including loss to biodiversity.
This is a new industry, and we have a unique opportunity to address these environmental issues from the outset. We can find out how far we can push the technology and the operations to achieve the goal of deep-sea mining while causing the least environmental damage.
IHC have designed the seafloor nodule collector, taking into account the environmental work carried out in the project. The first vehicle developed was the Apollo 1 to test functioning of the propulsion system. Its successor, the larger Apollo 2, was developed to test general functioning and the collection system. This vehicle has 4 tracks, increasing maneuverability, efficiency, and reducing the sediment plume. It was important to limit its weight. To achieve this, it's made of lightweight materials. It's electrically powered to make it as energy efficient as possible. And after testing both a mechanical and jet collector, the jet collector option was chosen for its robust design. The full-scale vehicle will have all the basic features of the Apollo 2, including being all-electric and the 4-track layout. The jet collector will be a 16-meter wide modular design. The seafloor nodule collector needs to be lowered to around 5 kilometers below the ocean's surface. The collector is connected by an umbilical cable that transmits power and communication signals. It's also connected via a vertical transport system or riser pipe that will transfer the ore from the seabed to the surface operation vessel. The seabed is composed of soft muds with nodules lying strewn across the surface, which are removed from the mud as part of the mining process. Water jets blast them free, but also create clouds of unwanted sediment that are sucked up to and released as a plume behind the vehicle. Each hour of operation will recover around 400 tons of nodules from a mined area of approximately 0.03 square kilometers. Similar to other extractive industries, small animals living in the sediment and attached to the nodules will be removed. In an area such as the Clarion-Clipperton Zone, recolonization may take a very long time. We designed a new method of separating nodules from the sediment inside the collector vehicle, using an inclined tube in which nodules slide to the bottom. The sediment is ejected at the top of the tube, passing to the rear of the collector, where it's released. This mostly deposits on the seabed behind the collector, but some remain suspended in the water, forming a sediment plume that's carried away from the mine site, where it may impact the seabed fauna. We developed a computer model to help predict how far the plumes would spread. The results show that the coarsest sediment grains settle within several kilometers of the mining site. However, despite very weak local currents, the finest grains are transported over much greater distances. We looked at whether compaction of the seabed by the collector would hinder recovery of life within the sediments, and concluded that other factors such as deposition of the sediment plume behind the vehicle would be more important. From the collector, the nodules plus some sediment not removed are flushed into the jumper hose, which forms a flexible connection between the vehicle and the riser pipe. They are pumped up on their 5-kilometer journey to the surface vessel. Pumps are located every kilometer and will generate noise. As very fine particles cannot be recovered, we needed to determine the degree of abrasion and fragmentation of nodules during transport. We found that only a small fraction would be lost. We looked into the possible impact of noise from the collector, pumps, and surface vessel. One of the conclusions was that pumps should not be located in the SOFAR channel, around 1 kilometer below the sea surface, as sound can transmit long distances here, and this channel may be used for long-distance communication by whales. The material arriving at the ship will consist of water derived near the seabed, sediment not removed at the seabed, plus nodules and a limited amount of nodule fragments. This material must be dewatered, as nodules need to be stored in a dry state. The removed water contains some sediment particles, which, when returned to the ocean, form a sediment plume, which is carried by currents and may impact animals living at different depths depending on where it is released. Releasing this water near the seabed is estimated to have the least impact. The nodules are stored on the surface operation vessel, where they wait to be offloaded onto the bulk carriers. We looked at alternative transfer options. The nodules can either be re-wetted to be pumped in a wet state and then dewatered, or transferred in a dry state by conveyor, though this means the two ships need to be located close together.